Alice and Bob are playing a game of pool in a bar. Suddenly, Bob has an idea. He challenges Alice to cue the ball so that it ends up where it started and going in the same direction. After thinking for a while, Alice responds, "Easy, I just strike it right at the wall, making it bounce back and forth." Bob, feeling dissatisfied by Alice's solution, gives her a new rule. The ball must now collide with the walls at least 3 times before returning to its original position. Again, after a few tries, Alice figures out a way to do it. She places the ball in the middle right before the left wall and bounces it off the other 3, making the ball hit every wall once. After playing around with this concept for a while, Alice and Bob quickly become suspicious that there are infinitely many ways to make the ball end up where it started. As we will see, for any position of the ball, there are infinitely many periodic trajectories. To show this, however, we first need to make some assumptions. Assume that the ball is infinitely small, such that we can draw it as a single point. Just like in a physics class, we will not take friction into account, so once the ball starts rolling, it will never stop. Also, since corners are a bit tricky, we're going to treat them like the pockets of a pool table. The ball falls into the pool table and the trajectory ends. Now let's look at what happens when the ball makes contact with the side of the pool table. Realize that the collisions are angle preserving, meaning that the angle of incidence is equal to the angle of reflection. Notice that this would not be the case if we took friction into account. We will get back to this observation later, so keep it in mind. Before looking at rectangular pool tables, we will look at an easier case, a square table of 1 by 1. Notice that the periodic trajectories Alice and Bob found before still exist on a square pool table. Do you notice a pattern here? Bob realizes that they've only found periodic trajectories with an even amount of collisions. He asks Alice if she thinks it's possible to make a periodic trajectory with 3 collisions. She doesn't know, but is eager to find one. After some time trying, they agree that it must be impossible. Bob says, "Let's prove it." They grab some paper and start writing. Let's look at their proof. Suppose such a trajectory exists. Then, because it has 3 collisions, it forms a triangle. Name the inner angles A, B and C. This angle between AB and the side of the square we will label alpha. Remember that collisions are angle preserving, so this angle is also alpha. We find that B is equal to 180 minus 2 times alpha. The angle between AB and the top of the square is 90 minus alpha, because the corner of the square is 90 degrees. Again, the collision is angle preserving, so the opposite angle is 90 minus alpha. After some calculations, we find A to be 2 times alpha. Now remember that the angles of the triangle add up to 180 degrees. Plugging in A and B, we see that C is 0 degrees. This is a contradiction, since an angle of 0 degrees wouldn't form a triangle. We conclude that a periodic trajectory with exactly 3 collisions is impossible. Up until now, we have seen periodic trajectories with 2, 4 and 6 collisions. Alice and Bob have also proven that a trajectory with 3 collisions does not exist. They start thinking about the intuition that there may exist periodic trajectories for every even number of collisions. As it turns out, their suspicion is correct. But to prove that, we need to look at this problem from an unexpected perspective. If instead of reflecting the trajectory of the ball when it hits the wall, we reflect the table itself over the wall, we see that the ball keeps going in a straight line. Note that this is a straight line by our assumption that collisions are angle preserving. This concept of reflecting might be a bit difficult to wrap your head around, so we've given the walls each a unique color so you can keep track of which way the table is reflected. As we keep doing this, the ball keeps going in a straight line forever. But more importantly, you might have noticed that the pool table and its reflections start to form a repeating pattern. We can draw this pattern in the entire plane, which we will use to prove that Alice and Bob's intuition is right. Since the pool table is square, we can nicely put the corners in the origin and the points 1, 0, 1, 1 and 0, 1. This way of looking at it raises a pretty urgent question. Since the ball keeps on going in a straight line, how do we know when it has reached its original position? To answer this, we need to introduce a notion of equivalence. We need to have a clear understanding of when 2 points in the plane are the same in the context of the original pool table. Since we have constructed this plane by reflecting the pool table over its edges, we have that 2 points are equivalent when one can be placed on the other by reflecting it over the integer lines. Note that you may reflect multiple times. Now for the first step of our proof. We will place the ball at the point 0 alpha, where alpha is between 0 and 1. We will call this point A. Let's look at the points to which it is equivalent. We'll take this spot here and draw our trajectory towards it. If we count the number of collisions, which is the amount of times it crosses a wall, we see that this trajectory has 4 collisions. Note that since the ball starts on the wall, we only count that collision once. If we instead make a trajectory towards this point, we get 6 collisions. Notice how we still only cross horizontal integer lines twice, but vertical ones 4 times. This is because the y value of our target point is the same, but its x value is increased by 2. Every time we increase the x value of our target by 2, so does the number of collisions of our trajectory. Since we can do this an infinite amount of times, we see that there exist trajectories with 4 plus 2k collisions for every positive integer k. Let's dive a little deeper into the points equivalent to our initial point A. If we reflect this point over the line y equals 1, we get the point A prime, which is 0, 2 minus alpha. If we would then reflect A prime over the line y equals 2, we get the point A double prime, which is 0, 2 plus alpha. Note that the distance between A and A double prime equals 2. We conclude that all points equivalent to A on the y-axis are 0, y plus or minus alpha, with y even. Furthermore, since A is placed on the red line and the red lines are precisely the even vertical integer lines, we have that any point equivalent to A is of the form x, y plus or minus alpha, with x and y even. However, we will not be looking at points x, y minus alpha, since these create a trajectory that hits the corner, which was not allowed. We will not be proving this, but that might be a fun exercise for you to try yourself. As the other points are sufficient to prove our theorem, we will only be looking at those points. With all these lines and reflections, you might forget what we're looking at, which are trajectories within a pool table. So, just to review before we enter the final stage of our proof, remember that whenever the ball crosses an integer line, on the pool table it bounces off the wall. Also, remember our most important find up to now, which is that every periodic trajectory through our point A must end in a point of the form x, y plus alpha, with x and y even integers. And particularly, every point of that form is an end to some periodic trajectory through A. Now that we're all up to speed, let's look at the final piece of the puzzle. Take a random rational number, that is, a number which can be written as p over q with p and q both integers. We will use this number as the slope of a line that goes through A. The function of this line is given by y equals p over qx plus alpha. Now, let's look at some other points on this line. Define a1 as q p plus alpha and notice that a1 is on this line. We are looking for points equivalent to A, so this point isn't particularly interesting, because P and Q don't have to be even. So, let's go further along the line and notice that the point 2Q, 2P plus alpha is also on this line. We will call this point A2. This point is very interesting, because we now do have a point equivalent to A on our hands. See how this point is of the form x, y plus alpha with x and y even. This means that there is a periodic trajectory between A and A2. Furthermore, since this works for any rational number p over q, we have that there are infinitely many periodic trajectories through A. However, I can tell you're not completely satisfied with this proof, seeing how we assumed A to be placed on the red wall. So now, take any point on the pool table, and again, we have a slope of p over q. Notice that this trajectory will always cross the red wall at some point. Do you see why? For this point, we have already proven there exists a periodic trajectory for the slope p over q. Since our original point is on this trajectory, we have also proven it for this point. Let's go back to our friends Alice and Bob. They're not all that impressed with our proof, since they're playing on a rectangular pool table, not a square one. There is a pretty simple fix for this, however. We can use a transformation to stretch or compress the square into any rectangle we'd like. If you want to have a rectangle whose coordinates are at 0, 0, 0a, ba and b0, then we can use the transformation that sends xy to b times x, a times y. We name this transformation f and its inverse g, which does the opposite. We can take our point A in the rectangle, transform everything into a square using g, then find our trajectories with slopes p over q, and transform everything back to the rectangle using f. We will find that our transformed slope a times p over b times q is the slope to a periodic trajectory through a. Alice and Bob can now finally rest knowing that their suspicion has been confirmed. However, there is still more to this topic than we've shown here. What about other shapes of pool tables? Triangular ones? Circular? Or even polygonal? For most of these shapes, mathematicians have not even found a single periodic trajectory. It's safe to say there are still tons of pool-related problems for Alice and Bob to bet over.